Hope you enjoy your break. Let's go back to this, as I said, beautiful equation. So we have seen the foam, the glitter. We're going to look at the molecule, air molecules, or Rayleigh contribution, which for me will be the last part of the what I consider pre-processing. So LR, so R for Rayleigh contribution, so it's due to the gas molecule in the atmosphere, basically the air molecules. The scattering due to test molecules depends of their size. And their size are way lower than the wavelengths. So you have this kind of scattering. So the light is arriving like that. You have your particle, and the light is going to be back scattered and forward scattered. As I showed here, where we have the green light due to this Rayleigh contribution, there is huge contribution in the blue and a huge decrease for higher wavelengths. So it's what you see here. So huge contribution of the Rayleigh scattering in the blue and an exponential decrease towards the near infrared. And this explains something that you see every day, or almost if you live in Villefranche, when you look at the sky. How is the sky today? Blue. Why is it blue? So I'm going to repeat my question. Why is the sky blue?
It's the dominant scattering.
Exactly. It's because of that the sky is blue. And why the ocean is blue? Pareil, j'entends. I can't hear when you don't be shy. Bon, if you have the answer at some point. So, as I showed, keep in mind that the contribution of the Rayleigh, or gas, air molecules, as I showed, it's 50 to 90% of the total signal measured by the sensor. So it's a huge contribution, which means, again, sorry for repeating myself, that's what we're looking for is very it's small. 1 point for you. Which, again, sorry for repeating myself, which makes atmospheric correction very difficult to do. And I know most of you will never use atmospheric correction. You will be very happy to use ocean color images, thinking that they are perfect. Keep in mind they are not. But you will do a good job in all cases using them. So we have to remove this Rayleigh contribution, which is 50 to 90% of the signal. How do we do that? OK, it was there. So a lot of equations. I'm not going to go into details, just for the sake of putting a bit of physics. So you can determine the concentration of air molecules that is defined by this Greek symbol, tau, which I will say it after, it's the optical thickness. So basically, the concentration, it's a proxy of concentration of air molecules in the atmosphere. So we can link this concentration to, very easy, to the wavelengths at which you're looking at the atmosphere. And so this is for 1 atmosphere of pressure. Obviously, when you look at the atmosphere from your satellite sensor, it's not always, or it's not at 1 atmosphere of pressure. So if you know the pressure of your atmosphere on your location, you have a very easy relationship between this radio optical thickness at 1 atmosphere of pressure to the pressure of the atmosphere you're looking at. Very easy, which is the pressure of your area over the pressure at 1 atmosphere of pressure. So,
Cédric? Sorry. I'm reacting a bit late to what you said about them not needing to do atmospheric correction, but the students will actually be doing atmospheric correction themselves in the last session of the day. You will all be running software to perform atmospheric correction for Landsat 8 and Sentinel-2, and it will be a practical application of everything you're seeing here. So you do need to follow this very closely. So.
No problem. Okay. Well, sorry, I'm lost. Okay, what you see here, just don't look at those ones. I don't know why I put those ones. So what you see here, it's a Rayleigh contribution as a function of wavelengths for a given geometry of view. So as before said, huge contribution in the blue and exponential decrease. Not going to go into details there. If you want to have, if you're really excited by that, if you want to do a lot of physics, you go to read this paper that is brand new in Optic Express. This figure comes from that, and you have all the calculation. So once you have your concentration of air molecules, you have a very easy relationship between the Rayleigh radiance and your concentration of air molecules, depending, again, at atmosphere of 1 pressure. So it's a very easy formula. And the good thing with the Rayleigh scattering radiance, it can be computed accurately. If you know the atmospheric pressure, obviously, as you need it here, but also you need to know the state of your ocean surface. So depending on the roughness, it's going to have an impact. And to know the roughness of your surface, you need the wind speed, which means, again, that you need ancillary data. And again, if you need ancillary data, they are not perfect, especially they come mostly from models. So it's going to impact your estimation of the Rayleigh contribution. But if you know perfectly your wind speed and your atmospheric pressure, you can accurately compute your Rayleigh radiance, which is good because, again, it's between 50 and 90% contribution of your top atmosphere radiance. Okay, we have finished what I call the pre-processing. So we have seen contribution of the foam, the wet caps, contribution of the solar reflections on the ocean surface, and the contribution of the air molecules. So now we're really going to enter, from my point of view, the atmospheric correction part. So to try to determine the quantity of small particles in the atmosphere. Still, don't forget what we want to estimate, the backscatter light due to the ocean. Okay. If we go back here, if we look at the situation when we have a low value of chlorophyll A concentration, if you look at the ratio of the contribution of the atmosphere to the top atmosphere signal, we saw and we said that in the near infrared, the contribution of the atmosphere to the top atmosphere signal was 100% almost. This is due, and it means that the water leaving radiance, or remote sensing reflectance, the water basketted by the ocean, is 0, or very tiny, 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 in the near infrared. So this is for the Sargasso Sea. You have in one axis the remote sensing reflectance, the wavelength in one axis, and you can see that if we have a closer look in the near infrared, that your signal is very, very small, 10 power minus 5 steradian per steradian. So it's how the atmospheric correction started 20, 30 years ago. It's to consider that the ocean is black, it's totally absorbent in the near infrared. I already spoiled you that we have been made progress for the past 20 years. But for open oceans, and low chlorophyll A concentration, the black pixel absorption is still valid. So I already mentioned it. We're going to use your sensor as different wavelengths between 400 and 900, basically, for all of them. And we're going to use several wavelengths to determine the quantity and type of aerosols. So you have several steps. So you have your pictures at a given wavelength of your region of interest. So this is a true color in the Adriatic Sea, if I remember well. So it's what you will see basically with your smartphone. This it's what you see at the top atmosphere at 412, 555, and 865 nanometers. As I said before, just before, in the near infrared, the contribution, bless you, the contribution of the ocean is 0 or negligible. So we can consider that the seawater is totally black, which is a famous black pixel absorption. Using testband, we can estimate the aerosol in the near infrared, which allow to determine an aerosol model. And when we know the aerosol, it's easy to extrapolate Z in the visible to, at last, get the parameter we are interested in, the water leaving radiance. So for a long time, and it's still valid, at least to my knowledge, for all-she sensor, we're using classical approach to use the black pixel assumption. What I just said, we can estimate the aerosol with 2 near-infrared wavelengths. I'm going to go into details a bit more after, and then we extrapolate this information to the visible. This black pixel assumption is very good for open ocean waters, but there are several problems. It doesn't, and until now, none of the atmospheric correction algorithm take into account the very strongly absorbing aerosols. You can have specific, as I will show if I have time, absorbing aerosol atmospheric correction algorithm, but for the operational atmospheric correction algorithm, none of them take into account absorbing aerosol because it's way more complicated. Second problem, and I think Heidi Diersen will talk about it, or she will talk about shallow water, so I suppose she will talk. So I said this works well for open ocean water when there is not a lot of chlorophyll concentration. Clear shallow waters, basically, like if it's clear, there is not a lot of chlorophyll. So this should work, except that if they are shallow and clear, you're going to have the sunlight is going to rebound on the bottom and will have a contribution. This classical approach doesn't take into account that. It doesn't work for coastal area when there is sediment, but I will show after how we can deal with that, because the assumption that the ocean is black in the infrared is not valid anymore. And even if you are in chlorophyll-dominated water, this assumption is no more valid if there is high value, or moderate, it depends where you put the threshold, value of chlorophyll, typically from Siegel et al. 2001, it's 1.5 milligram per cube meters. So after that, after this concentration, you can't really use the black pixel assumption. But it works very well, as we will see. So to solve this problem, we need to try to be, don't know if it's smarter, but try to do things a bit differently. And I will show after how to do that. So it's another way to say it. So black pixel assumption, the ocean is black in the near infrared. No contribution of the ocean for test wavelengths, which means that if you have already pre-processed your data, if you already pre-processed from white caps, from Rayleigh, and from glitter, your pre-processed signal, what we call the Rayleigh-corrected reflectance, is only due to the contribution of the aerosols in the near infrared. So you have here 3 images for the Western Mediterranean Sea of the Rayleigh-corrected reflectance at 670, 765, 865 nanometers. These wavelengths correspond to the CWIF sensor. So you have 2 wavelengths in the near infrared. So here, it's only the contribution of the aerosols, which means that if you are able to invert this signal, you will be able to estimate the aerosol optical properties and the aerosol model. And you have done 98% of the work. Because if you're able to estimate the aerosol models and aerosol optical properties, you will be able to estimate the contribution of the aerosol and the diffuse transmittance for all the wavelengths of your satellite. Obviously, it's not so easy. So, what is an aerosol? An aerosol, as I said, it's a very broad approximation, but it's like the phytoplankton. It's small particles in suspension in the atmosphere. Phytoplankton has small particles in suspension in the ocean. The medium is different. The particles in the atmosphere can be solid or liquid. To my knowledge, liquid phytoplankton don't exist, but maybe I'm wrong. And they are larger than the gas molecules. And such as phytoplankton, they can have size and shape that are very different. You can see here different examples. Here it's maybe like rectangular, a bit like diatoms, but here it's very irregular. So you can see, such as phytoplankton, the aerosols are very different in shape and in size, which means that they're going to absorb and scatter the light differently depending on the aerosol model. Same thing as for phytoplankton. Some of them, we can really nicely see them from the atmosphere, from top atmosphere sensor. Here, you can see here desertic dust. So here in the Mediterranean Sea, we are roughly here. So usually if you let your car in August here, if it's raining, your car is going to be full of dust. And here it's Western Africa, so also like coming from the desert. And those desert plumes go, after a few months, go to Hawaii. So, and here, along the east coast of US, you can have haze, you can see good. So you can see that they are different, just to see. Those ones are brown, those ones are more like maybe clouds, and they don't have the same extent. So they are very different in shape, in size, but they are also very variable in space and time. Less variable in space and time than what happens in the ocean. So we can define them by 3 parameters. First, the optical thickness tau. The only thing to remember, well, not the only, but if you want to remember something, and if you really hate equations or formulae, it's that it's a proxy of aerosol concentration in the atmosphere column. It goes from 0. If there is 0, there is no aerosols. And it can go up to 2 when you have really desertic, like a big plume of desert dust. Over the ocean, I think I have one picture. Roughly, the value of optical thickness are usually around 0.1 at 870 nanometers. And I think you can relate that. It's a bit like the KD, the diffuse attenuation coefficient. It's roughly the same thing, except that one is for the ocean and one is for the atmosphere. Second parameter is the angstrom coefficient. Things to remember. It's a proxy of the aerosol size. It's a bit like for the spectral relationship for BBP. BBP's wavelength over reference wavelength, power minus n. Anyway, it's related to the concentration of the aerosols. So it's this parameter. If the value is small, the aerosols are big. If the value is big, the aerosols are so high value, small aerosol, small value, big aerosol. If you have to remember. So it usually varies between minus 0.5 for maritime aerosols to value of 2 for pollution aerosols. Basically, it's a range. So optical thickness, concentration, Armstrong coefficient, aerosol size.
So can you just explain the optical thickness again? So it's so the measurement at 870, did you say, and then it's
For optical thickness, so I don't remember what I said. So for the value you...
I just didn't quite understand how that's determined. So
I didn't really...
you take a measurement at one wavelength and then you model it based on the extinction coefficient. Is that right or not?
Well, if you know the extension coefficient, you just... if you know at what altitude is your aerosol, you can integrate. But I just put the equation like that, but what I want you to remember is that the optical thickness is just a proxy of concentration. So, and it goes from 0 when there is no aerosol to 2, knowing that if you have value higher, that's 0.4, we have a lot of aerosol in the atmosphere. And then what I said, it's in a way, it could be, like as a comparison, in a way, it could be compared to the diffuse attenuation coefficients, the KD, for the extension coefficient. So just keep that in mind. We can, if you want more details, I can give you more details, but I didn't want to go too much in the detail, but for what I want you to remember, it's just optical thickness give an indication of the concentration of aerosol in the lower column. Armstrong coefficient, if you know your aerosol optical thickness, you can have an idea of the aerosol size. So low value of alpha, big aerosol, high value of alpha, small aerosols. So basically, maritime aerosols are big, like sea salt. So value of minus 0.5, roughly. And pollution aerosols, small aerosol, value of 1.5. It's a bit. And for the dust, here, it's around 0.6, 0.8. Then you have a single scattering albedo, which a proxy of how an aerosol, how it's going to absorb or scatter the sunlight. So it's between 0 and 1. If the albedo is 0, it's totally absorbing. If value is 1, it doesn't absorb at all. Most of the aerosols that we're going to look at or try to eliminate have values between 0.9 and 1. So which means that it's weakly or moderately absorbing aerosols. If you have value below that 0.9, it's starting to be strongly absorbing. And then you have the refractive index. And the imaginary part is also related to particle absorption. Higher this value is, more absorbent is your aerosol. So it's usually those two parameters. It's usually the way you define your aerosols. But it's a bit like for the IOPs. BB is not the true IOP. It's more the volume scattering function. So it's the same for aerosols. You have the scattering phase function. You can see here function for aerosol and air molecules, and here for S particles. So forward backscatter, forward scatter, backscatter. So you also need, if you want really to characterize your aerosols, you also need to characterize the scattering flux function. What we're going to be interested in, it's optical thickness and angstrom coefficient. So you have to define your aerosol model. So the distribution of your aerosols, the function of number, surface, of volume, here in the function of diameter. So your aerosol can have different distributions. Most of them have bimodal distribution. And it's what we call, most of them have two modes. We call the coarse mode here for the big aerosol or high diameter, and the fine mode for smaller aerosols. So when you're going to do your atmospheric correction, so as I said before, you are in the near infrared. The signal measured by the remote sensor is only due to the presence of aerosols in the atmosphere when all the pre-processing have been made. Okay? So this contribution is only due of the concentration, the intensity of this parameter is due to the concentration of your aerosols, but also of the type of aerosol you have. Because as I mentioned, depending of the shape, of the size, also the type of aerosol, like what is being made, same thing that for PFT. The light is going to be scattered and absorbed differently. So what you need to do for your atmospheric correction is to determine the type of aerosol you have in your water column. So your concentration, the size, and when you have that, roughly, you use radiative tensor model to estimate your aerosol radiance, which means that to do your inversion, you need to define a priori some aerosol models. So for a long time, so as I said, I'm a bit NASA biased, but the principles are the same for black pixel absorption. The principles are the same for any sensor. The only thing that's going to change is maybe the type of aerosols, but the principles are the same. So if you're using MREN, don't worry. Everything I'm going to say for the black pixel assumption is valid for MREN. So you need to define aerosol models to be able to make your inversion. So it started with Shuttle and Fun, 1979. Shuttle and Fun are not as good as Cock and Monk, that I told you, paper from 1954. But their aerosol models are very good, or they were very good for a very long time, even if it was back then and it was not as easy at making measurement now. But they are very good approximation. So, not going to do into details, but it's a mixture. So they make measurements of different types of aerosols. They measure their properties. So the way they scatter the light, how they absorb the light, and the concentration and size. And with all test parameters, you can define several aerosol models, which has been made, I should have put here, sorry, by Gordon and Wang, 94. And Gordon and Wang in 1994, using TESS aerosol model, defined 12 aerosol models, oceanic, maritime, coastal, portospheric. They are just aerosol models that are representative of what we observe over the ocean. They are not simple models, but they are very useful for our atmospheric correction. In 2010, so 20 years later, NASA decided that maybe the science improved a bit. So they changed aerosol models. That's more realistic because they are based on a huge network of measurements called AeroNet. So basically, spectrophotoradiometers from the ground looking at the atmosphere and making continuous measurements of the aerosol optical properties. And there are 1,000 or 1,500 stations all over the world. So you can have very precise aerosol models. So they are different because their distributions are different than the previous models. You can see different. But we keep, if you look here, you keep the tip C for coastal, M for maritime. I think it's easier to talk about maritime aerosol instead of saying that aerosol have this kind of distribution. So they defined a couple of aerosols, and what you have to keep in mind is before we had 12 aerosol models, now we have 80 aerosol models. So there is a better discriminations, and they are more realistic, which means that should improve the aerosol correction, atmospheric correction. So you need aerosol models to do your atmospheric correction. We are still in the near infrared. We are still in the black pixel absorption. We are still, as black pixel absorption, the signal measured by the satellite, it's only due to the aerosol component. So what Gordon and Wang, 94, I again forgot to put the reference. So keep Gordon and Wang, 94, very important paper for atmospheric correction. So you have two measurements in the near infrared. What Gordon and Wang did is that they defined an aerosol epsilon ratio, which is just the ratio of the aerosol, the measurements of the satellite at 748 or at 2 band in the near infrared. Gordon and Wang used the shuttle and fun aerosols, that there are 12 models, and they have modeled this ratio over wavelength for the 12 models. You start here, and what you can see, the good thing with test models, shuttle and fun, is that there is no overlap between the spectral epsilon as a function of the aerosol models, which means that you have your measure. It's easy to compute this ratio because it's only directly your measurements at the two near-infrared wavelengths. And so you have your measurements. You look here where the value of this epsilon goes, and you can extract quite easily your epsilon, and this epsilon is linked to an aerosol model. So exactly what I said, you have your two measurements in the near infrared. You have your pre-calculated value of epsilon for your 12 aerosol models. So this, it's pre-calculated. You calculate your epsilon with a 2 near infrared value, and then you go in your pre-calculated table to see where your epsilon value is the closest to one of the aerosol models. Is it okay for everybody? I'm simplifying the thing, but I don't know if it's reassure you, but so here you have the epsilon. So you look where is it closest to one aerosol models, and usually you're going to be you'll never be or almost never be exactly on one epsilon. You will be always between, so if you call 1 Tis1, 2 Tis1, you will be always between two pre-calculated epsilon. So what you're going to do, you're going to do a mean, well, a weighted mean between two aerosol models. And when you know aerosol models, you're finished. Because if you know your epsilons here, you can extrapolate it to the visible wavelengths, and you can estimate for any given wavelength the aerosol contribution, even in the visible. And if you know that, your done is finished, because you directly, at last, have the parameter that you want, the water leaving radiance, for all the visible wavelengths. So this, it's really how atmospheric correction works in open ocean water. Is it a bit okay how it works? Well, I'm there until Friday if you're already lost. So as I said, it's the same principle for MREN or ALCI, the European Space Agency humidity sensor. The aerosol model might be a bit different, but the principle is exactly the same. Water totally absorbent in the near infrared. You have pre-calculated tables of aerosol models, and you're going to pick in these tables to know your aerosol models. And when you have your aerosol models, you're done. So it looks very easy like that. And so that's what I said. You have your aerosol models. You can compute in the visible your aerosol contribution, the diffuse transmittance for all the visible wavelengths. So this, it's a water leaving reflectance. And then you know better than me, you can then estimate a lot of bioptical parameters. Keep in mind, it's only valid for open ocean, only valid for chlorophyll concentration below 1.5 milligram per cube meters, valid only for non or weakly absorbing aerosols. And the way it's done, you do first the atmosphere, and then you do the ocean. Which means that if there is a contribution of the ocean in the near infrared, you can't use this thing. And so you have to do it differently. Okay, so this, it's the principle of atmospheric correction. There is one thing I didn't talk about. It's how you compute the transmittance. So if we go back, here, we have seen that. We just explain how we remove this part. We have seen that, except that we didn't. I explained you what it was, but I didn't tell you how to compute that. So this is a direct transmittance. This is a diffuse transmittance. Direct transmittance because it goes all the contribution of the glitter goes in only one direction. While for the water-leaving radiants or white caps, you can have you have a diffuse scattering of this parameter. So it's why we use a diffuse transmittance. So how do we relate these parameters to the atmosphere? For the direct transmittance, it's a sun angle, so you know it. And so you need to know the optical thickness of the Rayleigh contribution, so air molecules, of the ozone, and the aerosols. So, which means that here, we need to know the quantity of ozone over your region of area. So again, it means that you need ancillary data. And so again, even if you know that and that perfectly, this, as you're going to use ancillary data, that's not perfect, is going to introduce an error in your estimation of the direct transmittance. But this you have estimated during the preprocessing. This you use ancillary data, and this you just estimate it using the near-infrared wavelengths. So you have all the info. You can remove this part. Diffuse transmittance. I think my equation is not right. I think it's the invert. So the diffuse transmittance is basically the attenuation of your signal between the surface and the top atmosphere. So it also depends, and for the sake of putting equations, it depends, as I mentioned before, that it depends of the geometry of view. It's going to depend, same for the direct transmittance of the Rayleigh optical thickness and ozone. But then it's going to depend, contrary to the direct transmittance, to the type of aerosol you have in your water column. So this is the albedo, the way, as I defined before, the way an aerosol model is going to, well, not the way, but the percentage of, in a way, the percentage of light that's going to be absorbed by a given aerosol. And this is linked to the phase function. But if you know your aerosols, this can be computed easily. And so you can compute the diffuse transmittance easily, which is the case when you look at open ocean waters with a black absorption. As I said before, when you use a near-infrared wavelengths to determine the aerosol. So this is known, and so it's easy for the black pixel absorption to compute the diffuse transmittance. And so you can have beautiful pictures of ocean color all over the world and over the years. So this is a chlorophyll A concentration. As I said, it's a historical product of remote sensing of ocean color. And so then you can globally study the ocean color, thanks to the atmospheric correction. You can have, I'm not going to entail regional studies over the year, seasonal variations. The only thing that I have to mention, it's we are seasonal dependent. If you can see, if you are in winter in the northern hemisphere, you don't have data here, while you have in spring and summer, and it's the contrary in the southern hemisphere, just because the Earth don't rotate vertically, but with an angle. As I said, I was going to talk about atmosphere, and we have secondary products thanks to ocean color. As we estimate the aerosol models, we can, from ocean color data, here chlorophylla for Cocorico French ocean color sensor, we can also estimate the distribution of the aerosol optical properties all over the world the same way that we do for ocean color. So here for the concentration of aerosol, here for the size aerosols, and you can see, as I said, if you have dust, you have medium, small aerosols, and if you have pollutions here, for instance, or here, you have bigger aerosols. Just for information, that we can also study. So for people that make aerosol atmospheric correction, can sometimes be useful to look at a lot of the image optical properties to know the distribution of the aerosols. Anyway, so everything I said for the moment for atmospheric correction was dedicated to open ocean waters. Now we're going to see how we can study turbid coastal waters. As I mentioned already, it's way more difficult for all those reasons that we're not going to see all of them. We're going to see some of them, and I will let you, look by yourself, or I could give you references if you want to have more info about one of the subjects I'm not going to talk about. So what I'm going to be interested in now is to look at this part. So suspended sediment and sedum contaminated turbid water, and when we have to estimate the contribution of the ocean in the near infrared. As you can see here, it's a spectrum I showed you before when I explained you the atmospheric correction in open ocean. Now if you go in the Mississippi River Delta, you can see a spectrum of the remote sensing reflectance. So low values in the blue, high values in the red, and now non-negligible value of the remote sensing reflectance in the near infrared. If we zoom here, you see the difference between a very low chlorophyll concentration water and a sediment contaminated water. So the problem, it's for test water, we can't use the black pixel assumption anymore because of the contribution of the atmosphere, of the ocean in the near infrared. So we need to find a way to be able to deal with a near infrared remote sensing reflectance. So for the past 20, 15 years, people try to do that. You have here an almost exhaustive list of algorithms classified on their main hypothesis. So you have different hypotheses. You can see that there are a lot of algorithms. And so the tricky part is to which one I'm going to choose for my study. So I'm going to describe a couple of them quickly. I'm not this one is interesting, Wang and Shi, because it's using wavelength after 1200 nanometers, what we call the SVIR, the shortwave infrared bands. But the principle is exactly the same as the Gordon and 194 papers that I just described, except that instead of taking two near-infrared bands at 750 and 850 roughly, they took bands of 1200 and 2400 nanometers. But the principle is the same. So NASA, so I'm going to describe two algorithms, and one will be from Kevin, and that Acolyte is based on, if I don't say stupid thing. So how can you take into account this near-infrared contribution of the issue? So the way to do it is try to model a near-infrared remote sensing reflectance and try to remove it through different processing. So it's what they do. This summarize a bit that. It's what to scare you, or to say I'm starting to be hungry. There are still 30 minutes. I'm going to die. So it's a good summary of what happens for NASA. It's what it says with letters. So basically, it's an iterative process. So what they're trying to do is to look at the atmosphere, then to estimate the ocean, then to remove the ocean, to estimate the atmosphere, and so on. And try to adapt the near-infrared. So they use the bioptical model in the near-infrared on one given wavelength at 667. And they use, because you have to start from something, they start with the black pixel absorption to have a first estimate of the atmosphere, to be able to have a first estimate of the near-infrared contribution of the ocean. And then you have an iterative process where you adapt at each iteration the near-infrared water-leaving radiance. Second way to do it, so the first way was to correct model for the non-negligible remote sensing reflectance. The second way is to make an absorption on the aerosol and water contribution. So Riddick et al. 2000, and Kevin will be able to correct me if I say stupid things. So what's the basic of this hypothesis? The basic is to consider that over a given region of area, like a small region, that the aerosol and the water doesn't change. Or at least the ratio of the near-infrared water-leaving reflectance and the near-infrared aerosol reflectance is constant, are constant, over your region of area, which it's represented by these two parameters. So alpha is the ratio of the water-leaving reflectances at two near-infrared reflectances. Whatever you image, this parameter is constant. But not what? No. It's equal to a constant, but this constant depends of the sensor you're going to use. So if you use CWIF or MERIS or MODIS, this constant is different. But it's the same constant for any images of a given sensor. Then you define the famous epsilon that I just showed before. That's from Gordon and Wang. Okay, this epsilon. which is the ratio of the aerosol reflectance at 2 near-infrared wavelengths. And you calculate, so this epsilon is also constant over your region of interest, but contrary to the contribution of the ocean, it has to be calculated for your region of interest. And I think it's what they're going, Kevin? It's what they're going to do tomorrow.
Yeah, at 4 o'clock today, actually.
Oh, 4 o'clock today. So you're going to apply the atmospheric correction for Landsat and Sentinel-2. So suppose we have more details. So it's a 3-step atmospheric correction algorithm, because first step is to use the Gordon and Wang Cat 94 atmospheric correction to be able to estimate your famous epsilon. And that will help you to determine the contribution of the aerosols. And then, once you know epsilon for your region of interest, you can apply a Gordon and Wang 94 modified. I said I was NASA biased, but now I'm going to present an algorithm for MREN. And so this algorithm has been developed mainly to deal with the sun glint. As I said, for MREN, they thought that they were smarter than NASA, so they didn't tilt when there was sun glint. So most of images are sun glint contaminated, which is not very useful to make studies. And so this one is based on an optimization technique. But the interesting thing is that this one doesn't need any aerosol models. All the other algorithms, or most of the other algorithms, need pre-calculated lookup tables of aerosol models. This one doesn't make any assumption on your type of aerosol. Your aerosol contribution is just a wavelength-dependent polynomial equation that represents the Rayleigh contribution, the aerosol contribution, and the glint contribution. So it's a very, I would say, easy or nice way to try to avoid aerosol models, because, as I said before, if you have lookup tables, pre-calculated tables of aerosol models, you're not going to simulate every viewing view, every aerosol models, otherwise you're going to have a pre-calculated lookup tables of billions of cases, which will be unmanageable for operational processing. So at least with this one, you don't have any assumption. You don't need to try to look at the closest model, where you are to the closest models. And it uses what we call a spectral matching. It's also an iterative process. And I have to say it's a bit magical algorithm. I will show you why after. So this is just a comparison. You have 2 days, 2 following days, one with glint. You can see here the glint, contaminated portion. And the following days there is no glint. Exactly the same region, 1 day after. And we can consider that in 1 day, the ocean doesn't change much. So if you look here, the true color images, here, the water leaving radiance at 490. So you can see here patterns of here. And if you process with this algorithm over the sun glint region, it's what you obtain. And if you compare the pattern and the scale is the same for the same parameters, rho W at 490. If you look at the patterns, they are very, very similar. So you think that you do a good job. Then you compare with the operational NASA and ESA processing. So here it's Eastern Africa. So it's a 3-day average of water leaving reflectance. Sorry, I forgot to put. So we can see a lot of holes. Here's a glint. And magic. David Copperfield was there. And you have almost a 100% filled image. So it was first developed for open ocean waters, and now it has been developed for coastal waters. So here it's Vietnam, here, Mekong Delta here, and here it's a MREN NASA processing. So the one using this algorithm on the left, and here it's a processing with a polymer version for coastal waters. And again, you can see it's here. You have more data. That's the operational standard processing. And you can see that for the coastal waters, it's very comparable data. And so thanks to this algorithm, we are able to avoid the glint for MREN. So if you can get data for MREN using this algorithm, go ahead. Because here you see a 3D composite of chlorophyll A concentration with the MREN standard processing, and here with the polymer processing. And you can see that's where there is glint. You can really fill the data. And you have only 35% of the world covered with the MREN standard algorithm, while with the polymer, you have 73% of the globe that is covered. So there is 2 times more data with this algorithm, thanks to the correction of the sun glint. OK. So talking about coverage, if you take the standard products, NASA or ESA, and you look at the 2 most used, or that's what's been used, NASA sensor CWIF and MODIS, and ESA MREN, you look at the daily chlorophyll A, 4-day, 8-day, and monthly chlorophyll A, and you look at the coverage. Daily, you have MREN, thanks to sun glint, you have not even 8%, almost double for CWIF. And after 1 month, you covered most of the globe. So in 1 month, you can have a global view of the ocean color thanks to satellite. Here, it's mainly it's because of fires. Here, it's pollutions. Here, maybe pollution or upwelling. So the region that's not covered here is because it's type of aerosols that's not taken into account in the atmospheric correction. So that's everything I wanted to tell you about atmospheric correction algorithms. I hope I didn't kill you too much. For the next 20 or 15 minutes, I'm going to talk about 2 things. We have the algorithm, but we didn't talk if they are good or not. They look okay because you have nice color or nice pattern, but beautiful is overrated. So you have to check if they are good or not. So I'm going to talk about validation now. Then I'm going to briefly talk other issues that can occur when you study especially coastal waters. And if I have time, I will tell you very quickly what are the tools you can use to process satellite images. So first, validation. How do you validate atmospheric correction? You do what we call match-up analysis. So it means that you collocate in situ dataset and satellite images. So basically, you have your in situ measurements. If there is a lens there, if you did a transect, you have in situ measurements, and the satellite go along the polar, and at some point is going to overpass your location of your in situ measurements. So the first things to do is to colloquiate the day you made your measurements and the day of the overpass of the image. So when you do that, you have to think about several things. It's if you are in coastal waters or not. In coastal waters, very often the process of movement, I would say, it's higher than in open ocean. Open ocean is very slow. Coastal water, every hour or 30 minutes, you can have changes. So you have to be careful of the time difference between the overpass of the satellite and the times you made your in situ measurements. So Bell and Wardle in 2006 put a framework for doing matchups, but this framework has, especially if you study coastal waters, has to be adapted to your location. So most of people use 3 hours. 2 hours is perfect for open ocean waters. It might be too much for coastal waters. So you want to decrease 1 hour, maybe 30 minutes. It's very highly variable. And then what you want to do, you have your in situ measurements. Basically, it's done there. But the pixel of your satellite for classic ocean color images is at the best 300 meters. So you're going to compare the location of in situ data over 1 meter to 300 meters. So what you want to do to try to have a satellite image that is representative of in situ measurements, what you want to do is to look at pixels around the location of your in situ measurements. So you're going to define a box of pixels. For instance, here it's 3 pixels by 3 pixels, centered of your in situ location, and you're going to extract the value for each pixel of your remote sensing reflectance obtained after the atmospheric correction. But then, Bell and Wardle define a 5 by 5 box. It might be too much for coastal waters, knowing that seaweed and muddies have a spatial region of 1 kilometer. In coastal water, it can be really too much to have a 5 kilometer by 5 kilometer box. So you might need to decrease your box. And then you have to decide how to calculate your mean value. You take a box of different pixels to try to avoid high variability. Because if you only select the pixel over your in situ location, you may have luck. That's the pixel of after atmospheric correction is very good, or it's going to be very bad, but maybe around is very good. So it's why you're using a box of different pixels to be able to calculate the mean value over this pixel box. And I wrote something at some point, it disappeared. Oh no, it's there. And so you have to define also how many pixels you're going to use to calculate your mean value. Because sometimes you're going to have all your pixels with a value of RS, but sometimes you're going to have clouds here or here, or sometimes you'll have only 1 pixel over your box of 3 by 3 pixels. So you have to define how many pixels you're going to take to calculate your mean values. At least 50 or 100 values to have really constraint, or 66 or 72.5, whatever. But this is going to constrain the number of matchups you're going to have. And usually you won't have to have as much matchups you want to have a good statistics. So keep that in mind. And also some of the pixels may have values, but will have a flag. So this is a flag provided after atmospheric correction by NASA. So for some pixels, you're going to have some flags. For instance, Isengate, observed radons very high, or presence of coccolith, blah, 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 or atmospheric correction is suspect. So you also have to look at the flags. And for MREN and ESA, they are also flags. They don't have the same name, but you also flag. So you can check before, you have to check before you're doing your matchup analysis, the flags to be sure that there is no problem in your estimation. And this, you do it on what we call level 2 or level 3 products, which I give you here. I'm not going to go into details, but basically what you do for atmospheric correction, you take the level 1 or 1B, which is the calibrated top atmosphere radiance measured by sensor, and to go for 1B to level 2, it's the atmospheric correction processing. And the level 2 gives you the derived geophysical variables. So typically, the remote sensing reflectance. So once you have defined all those criteria, there is still a last one. You can calculate a coefficient of variability, because maybe you're going to have matchup with 1 hour from your in image, overpass image, 1 hour from your in situ data, a 3 by 3, at least 50 or 60% of data. But maybe you're going to have a very high variability over your box, like factor 10 or 100 between pixels. So you calculate a coefficient of variability, which is simply the standard deviation of your pixels over the box, over the mean value. And you decide to take, this is to define, only matchup having a variability coefficient below 0.2 or 0.15, or depending what you want, and on which parameter. It's better, if you really want to have good matchups, it's better to calculate this variability coefficient for each wavelength of your remote sensing reflectors. But this constrains a lot, so it's going to really decrease your number of matchups. But at least you're pretty sure that the images obtained via the atmospheric correction is good, or there is no problem. So I'm going to show you a few results to give you the error on the atmospheric correction. Knowing that someone wrote, if I remember well, 20 or 30 years ago, that we wanted a 5% error on water leaving radiance, if I remember well. It's a dream. I spoil you first. It's a dream. I don't think it will ever happen. Because you can see here, so it's for MODIS, and here for MODIS too. So you have a very nice network of continuous measurements called Aeronet Ocean Color. It's mainly open ocean, and except here in Adriatic, in Baltic Sea, it's a bit observing. So you can see here for each wavelength, visible wavelength of MODIS and then near infrared, the visible and here is optical thickness. Here in y-axis is the in situ measurements for each figures, and in y the value estimated after the atmospheric correction. So for 100 matchup, and here for individual for different sites. Basically, what you can see, it's if you look at the errors, it's between 412, 36%, or to 20% at 677, and the error decreases with the wavelengths. So basically, the errors are quite bad at 412, between 20 to 100 or 200%, and are quite low at 490, between 490 and 550. And the trend is the same, whatever station you take into account. So this is mainly for open ocean waters. ESA made the same type of comparisons, but for 4 different atmospheric correction algorithms for only open ocean water in frame of the Climate Change Initiative Ocean Color. So they compare those 4 aerosol models. And here you see the comparison for only one wavelength, 560, for different algorithms. So basically, if you look at that, it's roughly good for all of them, or roughly medium good for all of them. It's difficult to see. So they defined metrics to estimate which one was the most stable. And so they had scores. Higher the score is, better the atmospheric correction algorithm here. And you should have the color code somewhere. It's not, anyway. So if you use MRES, try to use the MRES data which have been processed with a polymer atmospheric correction algorithm. Because with this run-orbit comparison, they show that it's in blue. The polymer atmospheric correction algorithm was the most steady one and the most accurate one. You can do the same thing for coastal waters, for seaweed, still with data from IONET Ocean Color. What I want to point to you, same for when you study when you evaluate atmospheric correction algorithm in turbid water, as I said before, at 412, you can have negative values, which is impossible, which means that the atmospheric correction really failed for test cases. So you can see here for 3 different algorithms, standard, NASA, Kevin-Rodick, and spectral optimization. We see here the mean square error as a function of wavelength. Here the relative error. And you can see that they are roughly all the same. As I said before, high errors at 412, error decreasing quite good between 490 and 550, and increases again at 670. So this, it's classic smiley error as a wavelength. And I'm going for 5 minutes. So I put a lot of comparison. I will let them in the slide, so we'll have them. So basically, my feeling is that almost all atmospheric correction algorithms over turbid waters are roughly the same. They are good enough. Some of them, some of them are optical water types dependent, so they work well if it's chlorophyll dominated or sedum dominated or suspended matter dominated. But their formulas are roughly all the same. Basically 50% error in the blue, 15-20% error in the green, and then in the red it increases. So what you have to remember. And I'm not sure we'll be able to achieve a 5% error, and I'm not sure we'll be able even to decrease by 2 times the error at 412. But it's just my point of view. So in the 5 minutes I have, 2 things that you have to remember. First thing, if you work on coastal water, it's the adjacency effects. And second thing, it's also on coastal waters, you have absorbing aerosols. As I said, absorbing aerosols are not taken into account in any atmospheric correction algorithm, operational or an alternative. Basically, it's a fly. So what is adjacency effects? It's basically, you have the land, you have your image, and obviously the sunlight doesn't stop when it reaches the land. And so the sunlight is going to interact with the land, and there will be a contribution of the land to the total top atmosphere signal measured by the sensor. So when you do measurement, when you do studies very close to the land, and when I mean close, you can see here the difference between, here you can see the contribution of the land to the top atmosphere signal. So it's not a lot, but if you look in the near infrared where you estimate your aerosols, if you are at 1 or 2 kilometers, it's up to 12-15%, which is not at all negligible as you use test wavelengths in the near infrared to estimate your aerosols. So you have, if you're more than 5 or 6 kilometers, it's okay, you don't need to really take care of it. But if you do studies closer to 5-6 kilometers, keep in mind that your results of validation might be bad or not as good as you wanted because of the adjacency effects. The problem is that there are few tools that exist. You can see here, I'm not going to go into details, I'm going to tell you, it's a publication from Kratzer et al. If you have to all details, it's to correct from adjacency effects, it's very time consuming. And for what I saw, which means it was what it was, it can work very well, while it can work not at all. So my advice will be to keep in mind it exists, but put that aside, except if you want to do a PhD on that. But it's my point of view. So I gave 2 examples. There are 2 papers, one from Kratzer et al., one from PNAS 2014. So, and I think I have to finish just in 1 minute. So as I said, aerosol absorbing aerosol is the same as an adjacency effect. Keep in mind it exists, but nobody knows or wants or can do it. And if you want to process ocean color images, you have several ways to do it. You have CDAS from NASA, which has been created for seaweed, but it can process, I think, all the ocean color data, from the first one to other German and Indian sensor. And the good thing is that there is a forum. They are very active. You can ask all your questions. And also, which is very good, is that all the codes of their algorithm is open. It's open source. And you can also implement your own algorithm in the software. For MREs, it will be updated. But for MREs and Sentinel-3, you have the SNAP. Sentinel-3 toolbox that is also freely available. I think you can also implement your algorithm, but I don't think it's so easy as NASA. And so for people that want to work with Sentinel-2 data, use that. And you have an alternative option, which is Odessa. And you can do several things. You can download your online processing of MREs, but also there is software to process the data. And the good thing, like CDAS, is that you can implement your own algorithm in an easy way. And everything I didn't talk about. And that's it.
One comment I would like to make on the, it's a personal view as well to some extent on atmospheric correction, because what I would call atmospheric correction is, what you have presented at the beginning, to try to find a spectral range where the ocean is black, then you determine the atmosphere, and then you remove that from the signal and you get, at the end, the marine contribution. So that's independent. And then you moved at the end to this more optimization techniques like the polymer and many others. And then to me, the terminology atmospheric corrections become, to me, a bit not so well adapted, because then you couple the two, and at the end, you don't do independently the atmosphere, and then you look at what's remaining, which is the ocean. You have an atmosphere model, you have an ocean model, and you just try to, separate the two as best as you can. So then it's to me, a bit different. It's it's working well, but it's producing something a bit different. And sometimes even, and I think that's the case with the polymer, the water-leaving reflectance that you get at the end is computed. So it's a modeled value from the model which is embedded into these optimization techniques. So there are a number of things like this which are difficult when you come to optimization techniques, and then the atmosphere and oceans are not completely decoupled in the process. So I don't know if you share this point of view or not.
In a way, I share it, but for me, when you study turbid waters, as there is a contribution of the ocean, you're not obliged, but almost to have coupled. So I understand your point, but I know it's terminology. It's always a fight.
Questions? Okay. Yeah.
I would just comment that for example, the Modus Aqua sensor collects 1.5 terabytes of data a day. And then there's this list of another dozen sensors that NASA gets the data on and has to process. So the major constraint here is that the whole process has to be extremely fast with no human intervention, completely automated. Well, that means that you have to make a lot of simplifications and a lot of assumptions about all these different pieces. So there are often better ways to do things. We can do better than Cox-Monk for how you model sea surfaces, but it would cost so much computer time, it's not reasonable, and maybe you only get a 10% improvement anyway. So in all of this stuff, you look at it and you think, man, they've simplified this so much, I don't understand how any of this works. And it's really kind of a miracle that any of this ocean color remote sensing can actually be useful. Clearly it is, but it's nothing short of a miracle considering all the complexities of the atmosphere and the ocean and all the simplifications that have to be made in order to do this on a routine basis. And when I wrote this report recently for how NASA does things, I was shocked that there's all these papers by Howard Gordon and other people on how to do absorbing aerosols. But when it gets down to what NASA actually does, in July of 2016, they assume all aerosols are non-absorbing. Why? Because when they look at those two IR bands at like 750 and 865, you can't look at those two bands and say, oh, I have an absorbing aerosol, I need to do what Howard Gordon said in this paper over here. They simply say, we're just going to use these aerosol models, get this little extrapolation thing that Cédric and you know, we put out the water dating gradiences, and now you, the user, come along and say, well, gee, they're negative at 412. That's nature's way of telling you that NASA's assumption that it was a non-absorbing aerosol was wrong. So now you run CDAS and do your own atmospheric correction for your image, and you can do the absorbing aerosol part however you want, and you'll get a better image. But NASA can't afford to have some guy look at each image and say, oh, you know, looks like there's dust from the Sahara here, we'd better go do this other processing. It's really a tremendously complicated business. And of course, NASA will do a lot of things exactly like you saw here, and some other things, well, they do it a little differently than ESA, and then the Chinese will do it differently, and the Koreans will do theirs differently. So good luck, man. I've now, after spending like 6 months figuring out what NASA does, I never want to see atmospheric correction again. It's all yours. The report's there, read it. If you had a question, send it to the NASA folks.
Okay, I guess that's a perfect conclusion.
So I think there are few students are going to quit in later today.